Hey folks, welcome back to 7.5, part 5. And in this video, we're going to talk about solving trig equations with identities, all right? So we've learned a lot of identities and we've used them to verify other identities, but we can also use them to solve equations, okay? So we have 6 examples here. We're going to do a few of them here, but some of the other ones will be left for extra credit opportunity, okay? So let's get started with number 9 here. All right. I see a quadratic situation here. Sine squared. But this is not sine. So I can't just factor, right? But what I am going to try and do is think about what identities I could use here, okay? Because if I can make this and this both sine, or this and this both cosine, then I could factor, and that would be nice, okay? So I'm going to think about all the identities I know that involve sine squared. And the first one that comes up into mind is the Pythagorean one. All right, and in particular, we have sine squared x plus cosine squared x equals 1. Now, we know that's true, but what is also true is that I can subtract cosine squared to both sides and say that sine squared x equals 1 minus cosine squared x. And what that means is everywhere I see a sine squared x, I can actually replace it with 1 minus cosine squared. So that's exactly what we're going to do here. Okay, so 2, 1 minus cosine squared x minus cosine x minus 1 equals 0. Okay, now it would be really important for us to make sure we're writing down what we're using. So between that step and that step, I'm going to say the Pythagorean. Okay, this is what I mean when I say annotate your examples. All right, now I'm going to do a little bit of algebra and I'm going to distribute. So 2 minus 2 cosine squared theta minus cosine x minus 1 equals 0. And I can just say algebra. So I'm distributing here, or I could write distribute. That would be okay too. And now I'm starting to see the quadratic situation. But unfortunately, this cosine squared term is negative, and I don't really like to factor when the cosine square is negative. I'm going to take everything, I'm going to move it to the other side of the equation, and I'm going to get 0. Whoops. 0 equals 2 cosine squared plus cosine x. And let's see, 2 minus 1 is 1, but when I move it to the other side, it'll be a negative 1. And this will be some algebra, okay? All right, now I got to go ahead and factor, all right? So 0 equals, let's see, I got to think about how to split this middle term, how to write it in a clever way. So maybe I do my factoring off to the side here. I want 2 times negative 1 is negative 2 and 1. So numbers that multiply to make negative 2, but add to make 1 are 2 and negative 1. So really, I can write this as 2 cosine squared x plus 2 cosine x minus cosine x minus 1. Okay, I could change all the cosines to use if I wanted to, but part of this is also like helping us grow up a little bit in the way that we think about our math, that we can actually handle this with the u substitution in our brain, but not necessarily writing it out. Okay, now we factor by grouping. So I can take a 2 cosine x out, and I'm left with cosine x plus 1 minus 1 cosine x plus 1. And I get 0 equals 2 cosine x minus 1 times cosine x plus 1. And now by my zero product property, I can say that 2 cosine x minus 1 equals 0, and cosine x plus 1 equals 0. Okay. Now I should go back and annotate this. This is actually all algebra. Okay. Now, I think what makes this particular problem so hard is that, sure, we use the trig, but then we have a lot of algebra that we need to learn. And that is really the purpose of a pre-calculus class, is to combine topics that we know with algebra, because when we get to calculus, it turns out that the calculus part might not be that bad, but the algebra, we really have to know our algebra well in order to find success in calculus, okay? So now we're gonna go back to the trig part, right? I'm gonna take these two and I'm gonna continue up here just because I have sort of run out of room. And 2 cosine x equals 1, or cosine x equals 1/2. And that I can solve using my unit circle. So now we're back to the trig. X will be, let's see, where's the x value of an angle 1/2? That's pi over 3. And 5 pi over 3. So these are two of our solutions over the interval 0 to 2 pi. Now let's grab our other equation, cosine x plus 1. Okay, so cosine x plus 1 equals 0, so cosine x equals -1. And where does x equal, where's the x value equal -1? Well, it turns out there's only one place, and that's at pi. So these three are my general solutions. Now if my specific solution. Now, if I were to go ahead and graph these on a unit circle, I would find that none of them are exactly halfway from each other. So for my general solution, I am going to have to write them all separately, each one with its own 2 pi k. And for all of these, k is an integer. Okay, so a good example of when we use our Pythagorean identity to go ahead and solve. All right, I'm going to leave this one here as an extra credit option. All right, if you'd like to come to office hours and talk to me about example 10, that would be fine. All right, let's move on to 11. I think we'll do 11 together, okay? So 11, I notice that they all have cosines, but nothing's squared. So I can't necessarily think about this as a quadratic situation, okay? But one thing I do notice is that I have a cosine double angle, all right? And so it might be useful for us to remember that the double angle for cosine actually has 3 options, right? So we can say that cosine 2 theta, we can say that cosine 2 theta is equal to 1 minus 2 sine squared theta. That's one way we could say it. We could also say that it's 2 cosine squared, let me use thetas, not x's. 2 cosine squared minus 1. Or our third option is that we have cosine squared theta minus sine squared theta. All right, this is the one that looks kind of like the Pythagorean, but that minus sign there makes all of the difference. Now, I think a question that we might have is like, how do we know which one to use? There's so many options. There's 3 options. And I would say it's worth writing them out and like, let's listen to this logic. I'm going to choose this one because I have just a cosine on the other side. I'd rather not introduce anything with signs in it, because that just might make things a little bit worse, okay? So my first step is going to be this. 2 cosine squared theta minus 1 equals cosine theta, okay? So in other words, I'm taking this and turning it into this. And the way that we annotate that is we say cosine double. Okay. Now I see a quadratic. 2 cosine squared theta minus cosine theta minus 1 equals 0. Okay. This, my friends, is going to look a lot like this previous question we did, right? We have something that we're factoring. It's just that the sign in the middle is different. So that's going to give us some different angle. Okay. So if we factor, we'll get 2 cosine theta, and I think we will get a negative here and a positive here. That means that 2 cosine theta plus 1 equals 0, and cosine theta minus 1 equals 0. So it's very similar to the previous problem, just the signs are different. All right. We want to look for where cosine theta is now equal to negative 1/2. So that's going to be theta is 2 pi over 3 and 4 pi over 3. And then we want to see where cosine theta equals 1. And that's where the x value is 1. So theta equals 0. Okay. It's important that we don't put 2 pi because 2 pi is not included in the interval. Only 0 is included. Okay. Now, I'm going to draw these on a unit circle. Let's kind of see what we've got for our solutions here, because if I can do without writing 3 separate ones, that would be really nice. Okay. So I've got 0, I've got 2 pi over 3 and 4 pi over 3. And one thing I noticed is that it basically splits the unit circle into 3 even pieces. So you know what we can do? We can just say theta equals 0 plus pi k over, 2 pi k over 3. We're taking the whole unit circle, the 2 pi k, and we're cutting it up into 3 different pieces. Another way we could write this is just 2 pi k over 3, because we don't need the 0, where k is an integer. Okay. So again, that being able to identify your identity and then doing a whole bunch of algebra is really sort of the flow of what we're doing here. Okay. I'm going to leave number 12 here as an extra credit option again. All right. And let's take a look at this last 2 examples and see which one we have. All right. So I'm going to go ahead and take a look at 13. Now, I'm going to give us a hint for 13, but I'm not actually going to finish the whole thing. All right. So I'm going to give us a hint on how to get started. Now, you'll notice we don't have a 5x or a 3x. Like we don't have a triple angle formula. That would be like 3x, or like a quintuple angle formula, like we have a double angle formula. Okay. So here's where we need to be a little bit clever. I can actually write this as sine of 4x plus x, right? 5x is 4x plus x equals sine of check this out. I'm going to make 3 out of 4 and 1 for x minus x. Okay. That, my friends, is the hint for number 13. These two should look like some identity that we've learned. And I'd love to see you take a stab at this one. All right, so extra credit. All right. Last one here. I think this is also along the same lines of some of the other ones we've done. And I think it's really important that we just practice doing these on our own. Okay, I really can't encourage you to do that enough. All right, so take the time, go ahead and try these out, see what you get, play around with things, ask questions, but try and work through them on your own. All right, because on exam 2, you're going to be asked to work through these on your own without any hints like, well, which identity should I use? Okay, so it's going to be really important that we learn how to develop that intuition for ourselves. All right, my friends, I will see you later.